Today we will learn more about physics. I prepare for you 10 facts with explanation. So get comfortable and let's go. The study of chaos theory explores deterministic systems with sensitive dependence on initial conditions, leading to unpredictable, nonlinear behavior. Chaos theory concerns deterministic systems whose behavior can, in principle, be predicted. Chaotic systems are predictable for a while and then appear to become random. The amount of time for which the behavior of a chaotic system can be effectively predicted depends on three things: how much uncertainty can be tolerated in the forecast, how accurately its current state can be measured, and a timescale depending on the dynamics of the system, called the Lyapunov time. Some examples of Lyapunov times are chaotic electrical circuits, about 1 millisecond; weather systems, a few days; and proven, the inner solar system, 4 to 5 million years. In chaotic systems, the uncertainty in a forecast increases exponentially with elapsed time. Hence, mathematically, doubling the forecast time more than squares the proportional uncertainty in the forecast. This means, in practice, a meaningful prediction cannot be made over an interval of more than 2 or 3 times the Lyapunov time. When meaningful predictions cannot be made, the system appears random. Chaos theory is a method of qualitative and quantitative analysis to investigate the behavior of dynamic systems that cannot be explained and predicted by single data relationships, but must be explained and predicted by whole, continuous data relationships. Chaotic behavior exists in many natural systems, including fluid flow, heartbeat irregularities, weather, and climate. It also occurs spontaneously in some systems with artificial components, such as road traffic. This behavior can be studied through the analysis of a chaotic mathematical model or through analytical techniques such as recurrence plots and Poincare maps. Chaos theory has applications in a variety of disciplines, including meteorology, anthropology, sociology, environmental science, computer science, engineering, economics, ecology, and pandemic crisis management. The theory formed the basis for such fields of study as complex dynamical systems, edge of chaos theory, and self-assembly processes. Did you know? Synchrony and entrainment are observed in various physical and biological systems where interacting components achieve a common rhythm or coordination. Entrainment was originally described as 2 pendulum clocks coupled through a wooden structure. Synchronization in this system was achieved via mechanical vibrations through the wooden coupling bar. Oscillations are also found in various biological systems and can operate at the molecular level or at the organismal level. Entrainment of these oscillations can occur through interactions between single cells, within a single cell, or between a cell and its environment. Entrainment depends on 2 basic conditions: the coupling strength between the oscillator and external input, and the similarity between the intrinsic frequencies of the internal oscillator and the external input in the absence of interaction. Generally, a stronger coupling strength and closer intrinsic frequencies favor entrainment, though the exact requirement varies in different systems. The entrained state, or locked state, is represented by a rational number p/q. After p periods of the internal oscillator and q periods of the external oscillator, the system returns to the same state. As the coupling strength increases, phase locking becomes possible at a wider range of external periods. Further increasing coupling strength may result in complex phenomena such as multi-stability, in which multiple entrainment modes coexist, and chaos. These are depicted by the overlap of different tongues. The transition between a robust locked state and a chaotic one has been observed in a classic example of periodically stimulated cardiac cells, in which a small variation of the period of the electrical stimuli caused a transition between normal and pathological behavior of cardiac tissue. The study of granular materials focuses on understanding the behavior of collections of solid particles relevant to fields such as geology, engineering, and physics. A granular material is a multiphase material made up of a large collection of closely packed solid particles surrounded by a gas or a liquid. Because the ratio of the volume of solid to fluid phases is very high, the particles are in very close contact with each other. The study of granular materials involves analyzing the properties and behavior of large groups of solid particles. These particles are not bound together in a fixed structure but interact with each other through a variety of forces such as friction, cohesion, and repulsion. This area of study is essential in various fields including geology, engineering, and physics due to the prevalence of granular materials in natural and engineered systems. In geology, understanding how granular materials like soils, sands, and rocks behave under different conditions is crucial for predicting landslides, sediment transport, and soil mechanics. Engineers need to grasp the behavior of granular materials in construction, transportation, and processing industries to design structures that can withstand the stresses and movements inherent in these materials. In physics, granular materials serve as essential model systems for studying complexity, phase transitions, and nonlinear dynamics. The behavior of granular materials often exhibits intriguing phenomena such as jamming, segregation, and pattern formation, making them a rich area of exploration for physicists. By investigating the properties and interactions of granular materials, researchers in these fields can enhance our understanding of a wide range of natural and artificial processes, leading to advancements in industries, technologies, and fundamental scientific knowledge. One of the pioneers of research on granular media was Osborne Reynolds. In his last paper, 1885, he tried to describe in over 400 pages nearly everything through the interplay of hard spheres. He introduced a concept of dilatancy, an effect we all unconsciously encountered while walking on a wet beach. The concept of topological defects, such as cosmic strings and domain walls, arises from symmetry breaking and plays a role in early universe cosmology. When a system undergoes a phase transition, symmetry can be broken, leading to the formation of topological defects. These defects are structures that arise due to the mismatch between the different possible states of the system and are associated with particular symmetries. In the context of cosmology, the concept of topological defects like cosmic strings and domain walls is significant. Cosmic strings are hypothesized one-dimensional structures that could have formed in the early universe during phase transitions. These strings are like long, thin energy filaments with immense density and are believed to have a crucial role in the large-scale structure of the universe. Domain walls, on the other hand, are two-dimensional planar boundaries where a scalar field varies significantly. They are another type of topological defect that might have formed during symmetry-breaking phase transitions in the early universe. Domain walls can affect various cosmological aspects, such as the distribution of matter and energy. Studying these topological defects resulting from symmetry breaking provides insights into the early universe's evolution and helps cosmologists understand the structure, dynamics, and evolution of the cosmos. By exploring the implications of these defects, scientists can gain a better understanding of the fundamental forces and interactions that govern the universe's development from its earliest moments. Want to know more fascinating science facts? Don't forget to subscribe so you will not miss the next video. And we'll keep going. Time crystals are a phase of matter that breaks time symmetry. In traditional physics, time symmetry implies that the laws governing a physical system remain the same whether time is moving forward or backward. The concept of time crystals, which exhibit periodic order in time, challenges traditional notions of temporal symmetry and has implications for quantum systems. The concept of time crystals represents a fascinating and unconventional idea in physics where systems exhibit periodic order not in space, as in traditional crystals, but in time. Time crystals challenge the conventional understanding of temporal symmetry, which states that the fundamental laws of physics are the same regardless of when an experiment is conducted. In a time crystal, the system displays a repeating pattern or oscillation in time without having to input external energy. This type of behavior goes against our usual understanding of equilibrium and thermodynamics, where systems tend to rest in their lowest energy state. The implications of time crystals extend into the realm of quantum systems. Quantum mechanics describes the behavior of particles at the smallest scales, and time crystals bring in a new dimension to this understanding. By exhibiting time translation symmetry breaking, time crystals introduce a novel perspective on the behavior of quantum systems under periodic driving. The study of time crystals opens up new avenues for exploring the dynamics of quantum systems and understanding how materials can exhibit unique properties when subjected to periodic stimuli. This research has the potential to advance our knowledge of quantum mechanics, potentially leading to the development of new technologies and applications in fields such as quantum computing and quantum information processing. Time crystals represent a frontier in physics where the exploration of temporal structures challenges our existing paradigms and paves the way for groundbreaking discoveries in the quantum realm. Let's move on to the next fact. The study of nonlinear dynamics and pattern formation investigates the emergence of complex spatial and temporal patterns in physical and biological systems. Nonlinear dynamics is the branch of physics that studies systems governed by equations more complex than the linear. Nonlinear systems, such as the weather or neurons, often appear chaotic, unpredictable, or counterintuitive, and yet their behavior is not random. The study of nonlinear dynamics and pattern formation delves into understanding how complex spatial and temporal patterns arise in diverse physical and biological systems. Nonlinear dynamics deals with systems where the output is not directly proportional to the input. Instead, there are complex interactions and feedback loops that lead to intricate behaviors. In many physical and biological systems, simple initial conditions can result in the emergence of intricate patterns and structures over time. These patterns can be stationary or evolving, periodic or chaotic, and often exhibit self-organization phenomena where order arises spontaneously from disorder. By investigating nonlinear dynamics and pattern formation, researchers aim to unravel the underlying mechanisms that give rise to these patterns. This field of study is crucial in fields such as physics, chemistry, biology, and ecology, where understanding the formation of structures at various scales is essential for explaining phenomena ranging from fluid turbulence to biological morphogenesis. The study of nonlinear dynamics and pattern formation provides insights into the principles governing the emergence of complexity in nature. By exploring how simple rules can lead to the formation of complex patterns, scientists can better comprehend the behavior of intricate systems and potentially predict their evolution under different conditions. This research not only enriches our fundamental understanding of natural processes, but also opens up new possibilities for designing systems with desired patterns and functionalities in various scientific and engineering domains. Did you know? Photonic crystals are periodic optical nanostructures that can control and manipulate the propagation of light and find applications in optics and photonics. Photonic crystals are periodic nanostructures that have the ability to control and manipulate the flow of light. These structures are designed with specific spatial arrangements of dielectric materials, creating a photonic band gap that restricts the propagation of certain wavelengths of light. By tailoring the periodicity and materials used in these structures, researchers can influence how light interacts with the photonic crystal, leading to a range of unique optical properties. Photonic crystals find applications in various fields such as optics and photonics due to their ability to control light at the nanoscale level. These structures can be used to manipulate light in ways that traditional optical components cannot, enabling the development of novel devices for applications including optical filters. Photonic crystals can selectively filter out specific wavelengths of light, allowing for the creation of optical filters with narrowband or broadband filtering capabilities. Microcavities. By introducing defects or irregularities in the periodic structure of a photonic crystal, researchers can create microcavities that trap light at specific frequencies. These cavities are essential for applications in lasers, sensors, and quantum optics. Waveguides. Photonic crystals can be designed to guide and manipulate the propagation of light waves along specific paths. This property is crucial for developing high-speed optical communication systems and integrated photonic circuits. Sensors. The ability of photonic crystals to interact with light in a controlled manner makes them ideal for sensing applications. Changes in the environment can alter the optical properties of the photonic crystal, enabling the development of sensitive sensors for detecting various physical and chemical quantities. The unique capabilities of photonic crystals make them valuable tools for researchers in advancing optical technologies and creating innovative devices for a wide range of applications in telecommunications, information processing, sensing, and imaging. Interesting fact: the study of dislocations in materials and crystals plays a crucial role in understanding mechanical properties and deformation processes. Dislocations are defects in the crystal lattice structure of materials that have profound implications for the mechanical properties and deformation behavior of solid materials. The study of dislocations is essential in understanding how crystals respond to external forces, deform under load, and exhibit plasticity. Here are some key points explaining the significance of dislocations in material science. Mechanical properties * dislocations affect the mechanical properties of materials by influencing parameters such as strength, hardness, ductility, and toughness. The movement and interaction of dislocations within the crystal lattice are central to how materials yield, deform, and eventually fail under mechanical stress. Deformation processes * dislocations are the primary carriers of plastic deformation in materials. When a material is subjected to stress, dislocations move and interact with each other, allowing for slip to occur along crystal planes. This process enables materials to undergo plastic deformation without fracturing. Strengthening mechanisms * understanding the behavior of dislocations is crucial for designing materials with specific mechanical properties. Different strengthening mechanisms, such as solid solution strengthening, grain size refinement, and precipitation hardening, work by impeding dislocation motion and interaction, thereby enhancing the material's strength. Grain boundaries * dislocations can interact and pile up at grain boundaries, affecting the overall mechanical behavior of polycrystalline materials. The structure and distribution of dislocations within grains and at grain boundaries influence the material's response to deformation and its fracture behavior. Defect engineering * controlling dislocations and other defects at the atomic level through techniques like alloying, heat treatment, and cold working allows materials engineers to tailor the mechanical properties of materials to meet specific requirements for different applications. By studying dislocations in materials and crystals, researchers and engineers gain valuable insights into the fundamental processes governing mechanical behavior. This knowledge helps in the development of advanced materials with enhanced properties and performance characteristics for a wide range of applications in industries such as aerospace, automotive, construction, and electronics. The concept of emergent phenomena refers to unexpected, collective behaviors that arise from the interactions of simpler components in complex systems. The concept of emergent phenomena encapsulates the idea that in complex systems, interactions between simple components can give rise to unexpected collective behaviors that are not apparent when solely considering the individual parts. These emergent properties are not directly derivable from the properties of the individual components or their interactions, but manifest at a higher level of organization. Here are some key points to explain the concept of emergent phenomena. Complex systems * emergent phenomena typically occur in complex systems comprising a large number of interacting elements. These systems exhibit nonlinear dynamics, feedback loops, and self-organization, leading to the emergence of new, often unpredictable properties at higher levels of organization. Simplicity to complexity * emergent phenomena highlight the transition from simplicity to complexity in systems where the whole is greater than the sum of its parts. As components interact and influence each other, new patterns, structures, or behaviors emerge that cannot be explained by examining the individual elements in isolation. Examples * emergent phenomena can be observed in various disciplines, such as physics, chemistry, biology, sociology, and economics. Examples include the emergence of consciousness in the brain, flocking behavior in bird swarms, traffic patterns in urban areas, and phase transitions in materials, among others. Non-reductionism * emergent phenomena challenge reductionist approaches that seek to explain complex systems by breaking them down into simpler components. Instead, emergent properties emphasize the importance of studying systems holistically to understand how interactions between components give rise to novel behaviors. Implications * understanding emergent phenomena is crucial for predicting system-wide behaviors, designing robust systems, and uncovering hidden patterns in nature. By recognizing and studying emergent properties, scientists can better grasp the intricate dynamics of complex systems and develop strategies to leverage or control emergent behaviors for various applications. In essence, emergent phenomena shed light on the notion that complexity can lead to novel and unexpected outcomes, illustrating the beauty and richness of interactions in systems where the whole truly becomes more than the sum of its parts. Solitons are solitary waves that maintain their shape and speed without dispersion and are found in diverse physical systems such as water, optical fibers, and plasmas. Solitons are a fascinating class of solitary waves that possess unique properties, notably the ability to maintain their shape and speed while propagating over long distances without dispersing or losing their integrity. These coherent structures are found in various physical systems across different scientific domains, including water waves, optical fibers, plasmas, and even certain biological systems. Here's a breakdown of the key points regarding solitons. Solitary waves * solitons are solitary waves that behave as coherent entities, unlike typical waves that tend to disperse and spread out over time. They can retain their shape and amplitude as they move through a medium, interacting with other waves without becoming distorted or dissipating. Nonlinear systems * solitons are often a feature of nonlinear systems where the effects of nonlinearity balance out the dispersive effects. This balance allows the soliton to maintain its form through a delicate interplay of dispersion and nonlinearity. Physical systems * solitons can be observed in a wide range of physical systems, including water waves, optical fibers, plasmas and fusion devices, and biological systems such as nerve impulses. In each of these systems, solitons play a crucial role in phenomena such as wave stability, information transmission, and energy propagation. Applications * the unique properties of solitons have led to their application in various technologies. In optical fibers, solitons are used for high-capacity data transmission due to their ability to travel long distances without losing signal quality. In water waves, solitons can form tsunamis that propagate across oceans without losing strength. Mathematical description * solitons can be described mathematically using nonlinear partial differential equations, such as the Korteweg-de Vries (KdV) equation or the nonlinear Schrödinger equation. These equations capture the balance between dispersion and nonlinearity that allows solitons to exist. The study of solitons sheds light on the rich dynamics of nonlinear systems and the intricate interplay between dispersion and nonlinearity. Their presence in diverse physical systems underscores the universal nature of these fascinating solitary waves, and their significant contributions to understanding wave phenomena and developing transformative technologies. That's all for today. Thank you for watching. I'll see you in the next video.